Okay, good morning, everyone, again. So today we have our second lecture of the course. So we will have week 2 lecture, design of axially loaded structure steel members. Okay, I will just wait for 2 minutes and discuss other stuff until other students join us. But today is our second week of the course. It will be about the design of axially loaded members subjected to tension force or compression force. So this topic, we will have 2 weeks in this topic, week 2 and week 3. Okay? And I want also to let you know that the assessment details of project 1 has been released. Have you noticed that? Because I think Michael asked last week about the project description. So the project description of project 1 or the assessment details of project 1 are here. And maybe we'll talk in details about this assessment in the class after the lecture. So this is the assessment details. And this is again a group project. So you need to form a group of 3 students. Okay, and work together on this project. This project is 20% of the total weight of the course. And also we need to make sure you are happy with the group members so that we don't have conflict or any confusion between the team members during the semester, because this group will be in project 1 and project 2. Okay, this assessment is due on the 7th of October at 9 a.m. Okay, so we'll leave the details to discuss later in the class. Just to let you know that we have released the assessment details. So let's return back to our course website. So week 2, we will talk about the axially loaded members, and in the lecture we have the slides and the class example, and in the tutorial we have 2 tutorial questions we will discuss together in the class. So let's start with the lectures note. Okay, can you see the slides now clearly? So this is the slides of week 2, design of axially loaded members, Shanks battle for confirming. So lecture 2, again, design of axially loaded structure steel members under tension and compression. Okay, as you know, axially loaded members means the member is subject to forces in the axis direction. This force can be tension like this one or compression like this one. Okay, the main thing, the forces are axially applied to the member. In this week, what you need to do, or after the end of this week, you should be familiar with the general design principle of steel design. And when we talk about steel here in this lecture, we are talking about structural steel or hot rolled steel. members, because as you know, half of the first half of the course will be about hot rolled steel or structural steel. Second half of the course will be about cold formed steel. And will be able to calculate and determine the section and member capacity of steel member subjected to tension force and compression force according to the Australian standard AS 4100. The latest version we have currently is 2022. I think some of you has already used this standard before in other courses, but so we will also explain or give more explanation about the standard formulas and the requirement of the standard. The outline of this lecture, or what are the uh, parts of this lecture covered by? The first part, the general design principle in structural steel design, will be any like including the loads and load combination are available or according to section AS, standard AS 1170.0, section 4, this for load combination, and the design of structural steel member subject to axial compression according to section 6 of AS 4100, and design of structural steel member subject to axial tension will be according to section 7 of the Australian standard for steel AS 4100. So AS 4100 section 6 for compression members and AS 4100 section 7 for tension members. Okay, so this is the outline of the section of the standards we are using in our lecture today. So let's start with the general design principles for steel design according to the Australian standards. So the first requirement of steel design is the stability limit state, which is for whole or part of the structure to prevent instability due overturning or uplifting or sliding. So if we have some explanation about that, this point here. So the first thing for the structures, one of the requirement is the stability requirement. The stability requirement means we need to make sure when we are designing our building that this building will not be unstable due to overturning. So this is the first issue we can have. Overturning means the building may rotate about this point, for example. So this overturning. Also, we are worried about sliding of the building. Sliding mean if we have strong forces like earthquake or wind or something, the building slightly slides. The third issue we can face is uplifting. So for example, if we have strong forces from below, uplift force, so maybe we have a problem of uplifting to this structure. So the three stability concerns we need to consider in our design are sliding and overturning and uplift. So the design or the principal designs for steel should consider the stability limit states for to prevent the overturning or uplifting or sliding. The second requirement or second criteria of steel design is the strength limit state design for components, members, or connections. So we need to ensure that the member capacity exceeds the applied loads to this structure or to this elements. Okay, so for example, if we have the capacity of the member, we should make sure that the capacity greater than the loads, so that we have a safe design in regards of strength limit states. If the loads exceed the capacity of the member, this means the member will collapse or fail. The third criteria we have is the serviceability limit state, which control and limiting the deflection, vibration of beam, bolt slips, and corrosion. So serviceability are meant more or are focused more on the deformation of the building, like deflection or vibration or bolt slips, and can be also considered the corrosion. To avoid or to make sure that our building is surfacely safe, we need to make sure that any deformation or delta should be less than the allowable deflection for this element or this member. So this, to make a safe design, we need to make sure that the deflection of the member should be less than the deflection of the allowable limits. These allowable limits are given by the standard, Australian standard. We will see that later, but just general concepts. And other criteria of design we may consider in some cases, like the fatigue. The fatigue happened due to repeated loading. So in some cases, like for example, machine or cranes and so on, the load itself is not critical for the member, so the member is safe in strength, but sometimes because the load is repeated regularly, so that's why we have another problem of fatigue. So the fatigue mainly due to repeated loading, and also in some cases of steel, we can have brittle failure of steel or cracking, and also in some types of structures which is affected to high temperature or fire. So we need to consider the fire resistance of the structure when we are designing it. So these are the general principles of the design of steel, structure steel, according to the Australian standard AS 1170.0 and 4100. So let's interpret that in equations or in formulas. Actually, our concern in this course will be about the two criteria, strength limit state and surfaceability limit state. So this is our focus in design, strength and surfaceability. So for strength limit states, or we can call it ultimate limit state, we are considering different load combination based on the applied load to the structure. So as you know, what are the possible loads to our structure? Can have dead load, the standard give it the symbol G, and we can have live load or imposed load Q, and we can have wind load W, or we can have earthquake load or E. So this is the possible load on the structure. And also one load not very common, which is snow or earth pressure or any sort of load like that from this types. We give it in the standard symbol S. So the design criteria according to strength limit state, consider some combinations of these loads because all this load will not be applicable to the structure at once or with the same intensity at once. So that we need to consider some load combination like what we will discuss now. So the first load combination, if we consider only dead load only, so G only on the structure. So what is the load combination? 1.35 G. So this is the first one. The second one, if we have G plus Q, but Q in this case is the total Q. So we have 1.2 G plus 1.5 Q. So this one case of live load, we take the whole live load. Another case is 1.2 G plus 1.5 psi L Q. So as you can see here, we have a factor called psi L. Psi L just to take the effect of long-term life load. So we can call this G plus long-term Q. Because we have life load is not a long-term load, but in some cases or some structure, we have some types of long-term life load. Another load combination is 1.2 G plus WU plus psi C Q. So in this case, we have the factor psi C instead of psi L. Psi L, L for long term, C here for combination. So C is a symbol or a factor for combination because we are combining dead load, life load, and part of the life load. But you have to make a note here that the wind load here is downward wind because we have two direction of the wind. Just quickly here, if we have a frame, for example, and we are designing the beam. We are focusing on the beam now. So the loads on the beam can be dead load or G, and we can also have wind load. So the wind load can be pressure or downward. So this what is considered in the combination here. So in combination D, the wind is downward wind. You will see now the difference in the next combination. So the next combination is for upward loading or upward wind. So all those for downward loads and number E for upward loads. So here in this formula, our wind load is upward or wind reversal. So in this case, because the wind is going up, so we need to consider less amount or less value of dead load for the critical case. So if we go to this slide here, another case for this frame, if we have the wind, instead of wind downward, the wind is going up. So we call this suction, and the wind here is going upward. In this case, let's just have technical issue. So in this case, we don't take the whole did load applied. Can you give me a second, guys? Sorry. Sorry, guys. Can you hear me now?
Yes, we can hear you, sir.
Yes, thank you. So in this case, the combination for G will not be 1.2. We will take only 0.9 of G. Here in this case, we will take 1.2 of G. Okay, so for combination number 4, the wind is downward wind, and for number 5, the wind is upward wind. Okay, the next load combination are related to earthquakes. So this also downward. So we have G plus EU, earthquake load, plus psi E Q. Psi E here is the coefficient for earthquakes, and Q is the life load. And we have another formula or same formula if we have snow or earth pressure and so on. So in this case, we have 1.2 G SU and psi CQ. So in this case, the parameter is psi C, and the factor for G is 1.2. Okay, if you notice here, for strength limit state combination, we have factors for like increasing or magnification factors for the load. So in this case, we are using factored loads. So this is the idea behind this method. We are trying to increase the loads because this is extreme failure case. So we need to consider high loads to avoid the failure. So guys, can you hear me now? Hopefully no problem. Thank you guys for confirming, and sorry for the disconnection that happened from my side. Okay, so let's continue now our discussion. So now these are the possible load combination we can have for strengths, and in our course we will focus on the up to here. So no wind or earthquakes. Again, this for earthquakes downward, and this also for snow and so on downward. So the only one upward is for wind here, reversal action. And the parameter for this combination is psi E, and for this combination is psi C. Okay, if we go to the standard 1170.0 for strength limit state combination, this how it looks like in the standard. So again, we have 1.35 G, 1.2 G, 1.5 Q, 1.2 G, 1.5 psi LQ, 1.2 G, and W psi CQ, and this upward load combination for wind 0.9 G plus WU. Any question you have for the load combination for strength? Do you have any question, guys? No? Okay, so let's go to the next part, which is before we go to the next part, just have a look on the factors. Scientists, guys. So let's have a look on the factors we got in the load combination. So we have psi S, psi L, psi C, and psi E. Psi S, as you can see, for short term loads. Psi L for long term. Psi C for combination factors. Psi E for earthquakes. So based on the load combination you are doing, you will find if it is psi S, psi L, psi C, or E. And for the distributed load, UDL, the factors are two types. One for floors, or a group for floors, and a group for roofs. If you are designing floor, so depend on what is the type of the floor, offices, parking, and so on. For example, offices. So if you are offices, so these are the parameters. So psi L, psi S 0.7, psi L 0.4, psi C 0.4, psi E 0.3, for example. If you are designing a roof, so we have two type of roof. Roofs that used for floor type, like for example, there is people accessing the roof and the people is designed to maybe hold events or whatever they use. So the factors in this case are zero point 0.7 and 0.4, zero point 0.4, and 0.3. So this for roof type. In for any other normal roof or for any other roof that is not accessible, so can be 0.7000, because all other roofs means inaccessible roof. So if the roof is not accessible, so not many people or no life load actually apply it to the roof in this case. Any question? Okay, let's go to the next part, which is the serviceability load combination. So the serviceability load combination, we will need this load combination for deflection or deformation check. So the importance of this check is that maybe if you are living under, for example, if we have a beam like this, so this beam is applied to loads, and we have a column here, column here. This beam is safe, so it will not fail. But in some cases, if the load and the span is too high, so the deflection is something like this. So if you are living below this beam, so you may feel worried that the beam will fall on you. So also part of our design, the serviceability or the look of the elements, so that the standard give us a limit, which is allowable limits. So our deflection or our deformation, like this here, should be less than or equal to the allowable limit, so that the building or the people are feeling safe under the building. So these combinations are G for long-term load dead load effect, G plus psi L Q for long-term effect. So these two for long-term, and we have others for short term, G plus psi SQ. As you know, psi S, as we discussed earlier, is for short term. G plus psi SQ plus WS for short term effect as well. Or if you are designing for earthquakes, so G plus psi SQ plus ES. So we are up to here. So these two are for short term effect. So if you are checking the deflection for long term, you have two combinations, G and G plus psi LQ. If you are doing short term, so we have G plus psi SQ and G plus psi SQ plus WS. Okay, have you noticed something here? The notice is we have here WS, and in the ultimate load combinations, we have WU. What is the difference between WS and WU? Do you know? So WU is the ultimate wind loads. Ultimate wind loads are calculated using AS, the standard AS 1170.2. WS is the serviceability wind loads. Serviceability wind load will be determined manually from WU. So WS equal to a reduction factor times WU. This reduction factor, we can take it as 0.66%. Okay, so to convert from ultimate wind load to serviceability wind load, we need to multiply by 0.66. So this is the notice or the note we have here in this load combinations, and this is how it looks like in the standard. The standard give it to us in this form. So combination of action for serviceability limit states, and the standard mention that appropriate combination may include one or number of the following using the short term and long term values. So you have G, psi SQ, psi LQ, WS, and ES. So you can make combination of them. So combination of them as we discussed like that. So G alone, G plus psi LQ for long term, and G plus psi S for short term, and so on. Okay. Any question, guys, about the load combinations? Any question? No? So after we know the requirement for the load combination, the next is the design concept or the design criteria for strength limit states. So again, as we mentioned, to achieve the strength limit state requirement, we need to have the capacity of the member more than the applied loads, or in different form, all member and connection shall be proportioned so that the design capacity is not less than the design action effect S. So in other form, S star or S prime less than or equal to phi RU, where phi RU is what? Capacity, and S star is the loads or the applied load. So this is the concept. We need to make sure that the capacity more than the loads. Okay, phi is a reduction factor or safety factor, which is zero point 0.9 for structure steel member, like this table here below. So it is like you know the capacity of the member, for example, 100, but for safety you will consider it as 90, so that you have safe margin due to any uh, imperfection in the manufacturing process and so on. So phi is a safety or a reduction factor for safety. This factor, phi, can be found using table 3.4 in the Australian Standard 11 4100. For member under tension, as you can see, phi is zero point 0.9 for all cases. For member under axial compression, for member and section capacity, zero point 0.9. For member under axial tension, zero point 0.9. For member subject to combined action, zero point 0.9. So for all type of loading or type of members, we have phi as zero point 0.9. For connections, it is ranging between zero point 0.6 and zero point 0.9. So we give more safety factor for the connection, so that if you look to the part of the table of phi for connection, it is zero point 0.9, for example, here, and zero point 0.6 in some cases here. So based on the connection, if it is pin connection, bolted connection, or welded connection, we should select our reduction factor phi based on that. Okay, so this is phi and the design concept for ultimate limit states. And for serviceability limit states, what are the criteria of design, or what is the suggested limit? So again, we need to make sure that delta less than delta allowable. So we will know later how to calculate the deformation or deflection for the member using manual formulas or software. But what is the allowable limits of deflection? Delta allowable is the allowable limit of deflection given by the Stolenis standard 4100 and 1170.0. So these limits are given in two standards based on some cases. So as you can see here, Appendix C of AS point 0, 1170.0, or this table here from AS 4100, table B1. So what is the suggested limits for the vertical deflection? So just to make sure that we are here in this case, we are discussing the vertical deflection of the beam. So we are in this case, we are talking about if you have a beam, so this beam will deflect due to applied load like that. So this deflection is delta, and this delta should be less than the allowable limits in the table before. So this allowable limits based on one criteria, which is if the beam supporting a masonry partition or not supporting masonry. If it is not supporting masonry, so the deflection limits is span over 250. Or if it is cantilever, so this for normal beam or simple beam. For cantilever, it is span over 125. So the deflection limit is 250 for simple beam. This for simple beam, and this for cantilever. Because the cantilever is more critical, so that's why the limit is lower. Sorry, because the cantilever is susceptible to more deflection, that's why the standard allowed more deflection. If the beam supporting masonry partition, so we are worried about cracking in masonry. So that's why the deflection limits are reduced. So the deflection limit here is span over 500 for simple beam, and for cantilever span over 250. And even more in some cases, as you can see here, it can be up to span over 1000 and span over 500 for the cantilever. So in normal beams or the normal conditions, if we don't worry about the member supported by the beam, so no problem to increase the limits. But if we are worried about, like for example, beam carrying glass window or something like this, so we are worried about cracking of the window, so we can use lower limits for the deflection. The other type of deflection we may have in our structure is the lateral deformation or lateral deflection. So the standard also give us limits for the horizontal deflection. We have two criteria for the limits. The first one is the relative deflection, horizontal deflection between adjacent frames at each levels should be span frame spacing over 200. And if the frame carrying gantry cranes, so it is span over 250. Okay, so these two main cases here. Another type of or another criteria or another limit for the deflection is the absolute. So here relative horizontal deflection, here absolute horizontal deflection of a frame shall be limited to the following. So if it has no gantry, so the limit is eaves height over 150. And if it has gantry cranes, so this limit is reduced to 250. What does this mean if we do so? First of all, before we explain the limits, here is the vertical deflection of beams. If we have a frame, so we can have, if we have lateral load, so we can have lateral deformation of the column. So we are now talking about the deflection here. So this is horizontal deflection. So the standard is given a limit for this one as well. So delta should be less than delta allowable for lateral deflection. Okay. So if we want to explain that, so if we have some frames like that, let's talk about these two frames. If we have lateral forces in this direction, so these frames can move horizontally like this. So this one is the reflection. So this delta should be less than eaves height divided by 150. So based on the second one here, so eaves height divided by 150. What is the eaves height? The height of the frame. So this is our eaves height. Okay, but the problem is maybe some of the frame deflect more than others. So for example, this one here. So what happened to the sheeting between them? Or what happened between the members, between them, girths and so on? So we are worried about the failure or cracking or whatever of the cladding or the masonry between them. So that's why we have another limit. This limit is based on what? The frame is basing. So the standard put another limit which is delta, but delta here is the relative between the two frames should be less than or equal to the frame spacing divided by 200. So this is the first one and this is second one. So this is criteria number A, criteria number B for the horizontal deflection of frame. Is that clear? Any question about this part? All good? Thank you, Michael, for confirming. Okay, guys. So now we can proceed to the next part, which is the design of tension member. So all the previous was some discussion about the logic and the requirement of steel design. According to 1170.0 and AS 4100. So now the next part is the design of tension member according to the Australian standard 4100 section 7. Do you have a copy of the standard or not yet? You will need to have to download or access the standard so that you can uh, like have a look on the formulas and the explanation of the Australian standard. So for tension member is any member, can be vertical or horizontal or whatever, subjected to tension force. So if we have a steel member subject to tension force, we need to use the formulas in section 7 of the standard. So in this section, we only consider the section capacity, which means the yield tensile failure of the steel member under tension. So in this design, we are only worried about the section capacity, which means the yielding or the tensile failure of the steel member. Because as you know, the stress strain curve for steel, something like this. So we have two limits of this. We have the first limit is F yield or sigma yield, and the other limit is Fu or tensile strength. So this is yield point, this is fracture or tensile point. So when you are applying tension force on this member, and this member is under tension, so we have two criteria: the yielding of the member or ultimate or tensile failure of the member. So the standard for axial tension, the design of axial tension, the member under axial tension force N asterisk shall be or shall satisfy the formula N asterisk should be less than or equal to phi nt. So again, N asterisk is the applied loads and phi nt is the capacity. So similar to the criteria, N asterisk should be less than phi nt. Where N asterisk is applied load, you will calculate based on your analysis of the members or the frame, whatever the member you are designing. So this is from analysis. The tensile capacity of the member, this part, will be calculated using the formulas from AS 4100, where phi is capacity factor from the table 3.4, and we mentioned that phi for all members is 0.9, and nt, the capacity itself, capacity in tension, will be equal to, or the definition is the nominal section capacity. So it is the nominal section capacity in tension according to clause 7.2. So if we go to clause 7.2, the nominal section capacity of a steel member is the lesser of 2. So we have two values. One value is nt equal to ag times f yield. So this criteria is for yielding. The other criteria or the other value of tensile capacity is NT equal to 0.85 KT times AN times FU. So this for what? For ultimate or the fracture capacity or the tensile capacity? Tensile or fracture. So this is the two criteria or the two values of the capacity of the member in tension. And this one, these two formulas are based on the diagram here of yielding and tension. Sorry, yielding and fracture. So the first formula, considering this part here, so the first formula, considering that area G or the gross area of the section, this is the gross area, will yield. The other criteria, fracture, means, for example, in the members, steel members, we have holes for bolts and so on. So the problem is, this is the weak point. At the weak point here, the area is not the whole area, not area gross. The area is area net. So here area gross, here area net. So at this area, we are worried that we can have a fracture here. So when we have a weak point, we are worried about fracture. That's why we are using FU. If we don't have a weak point, or in areas like far from the hole, so we are worried about yielding more than fracture. So yielding means all the area will yield at some point. So that's why in this case we are using this point here for F yield. So this is the logic behind the two formulas, and we have factors here. The 0.8 factor is a reduction factor or safety factor. KT is a factor, correction factor for distribution of the forces according to clause 7.3. So it is same concept if we hide these two. So area times the stress. But because we are worried too much about fracture, so that's why we add this 0.85, so a safety factor. And also because the applied load not concentrically applied, so that's why we need to apply a factor of correction for the distribution of forces. So we will see this now. So the definition of the parameter, AG is the gross area, F yield is the yield stress, AN is the net area. So again, if you have a hole, so area net will be the area excluding the hole. Okay, so this is what is meant by area net. Fu is the tensile strength of steel. So these are the two formulas. So again, in T or the capacity is the lesser of these two formulas. AGF yield and 0.85 KT AN FU. The factor KT or the correction factor KT based on the shape of the element. So, for example, if we are connecting an I-beam to, sorry, angle to a plate. So this is what is meant here. So if we are applying, like connecting two members together under tension, we're not from the same shape, or doesn't have same shape. So we will have some eccentricity between the two loads. So this eccentricity will affect the capacity of the member. That's why we need to have the factor Kt. So the factor Kt for angles, one angle is 0.75 for unequal angles, and 0.85 for other cases. For example, if you have a T section, T, this is T, section connected to a plate, so it is 0.9. So if you have a channel connected to a plate, it is 0.85. If you have two channels, so it is the eccentricity will be 0, so it is 1, for example. If you have two T's connected to a blade, so it is 1. If you have two equal angle connected to a blade, so it is 1. So this examples of KT based on the configuration of the element you are designing. And now we jump to the, do you have any question about the tension members? Any question about tension members? All good? Okay, guys, thank you. So now the next part is design of compression member or member under compression. So design of compression member, any member or column or strut that is under compression force. What do you think about taking a 5 minute rest? Do you want 5 minute rest? Okay, so we'll have 5 minute rest. So back in or back at 10:20 a.m. So you can have some rest, drink something. Okay, see you in 5 minutes. Okay, guys, I think we can start again. Okay, so now for the design of compression members, according to the Australian standard, section 6, for the compression member, we have two criteria for the design. The first one is the section capacity, considering local buckling or yielding of the member, and member capacity, considering the overall or global buckling of the member. Why? Because the member under compression has a problem of or susceptible to buckling. Or make it to the other side. So we are worried about buckling. And buckling, two type of buckling, local and global buckling. So local buckling considered by section capacity and overall or global buckling considered by member capacity. This is reflected in the like the formulas for compression member design. So according to the standard for axial compression members, a concentrically loaded members, concentrically means the load act in the centroid or the CG. So if this CG, so the compression load act in the centroid of the member. Subject to axial compression, we should satisfy the following formulas. N asterisk should be less than or equal to pi ns. S means section capacity. And the second one, N asterisk should be less than phi NC, NC for member capacity. Where phi again is 0.9, NS the nominal section capacity, NC the nominal member capacity. This issue or the buckling issue is not in the tension member, so that's why the design of tension doesn't include any member capacity problem or any member capacity formulas. So let's start with the nominal section capacity NS. How to find NS? NS will be calculated using this formula. So NS equal to KF times AN times F yield, where KF is a form factor here. So KF is a form factor. AN is the net area of the cross section. So A net we have seen before in the tension member. F yield already we have seen before in the tension member. So F yield strength of steel. AN net area. So what is KF? KF is the form factor here. So KF is the form factor relation between area effective over area gross. So KF equal to area effective divided by area gross, or AE divided by AG. So this is a factor to represent or to consider the local buckling effect on the section capacity. So this is the importance of this factor. We will see now how this is important. The idea is for steel members, due to buckling or local buckling, if we have member like this, so This member, for example, can be subjected to local buckling based on the dimension of the member. And the buckling happened due to the relation between the length and thickness of the member. So if the member, for example, uh, long and thin, so it is more susceptible to buckling. So the buckling is a relation between the length and thickness. So if we see the three parts of this uh, member, so this part of the flange, this part of the flange is subjected to buckling. This part of the flange, this part of the flange subjected to buckling. For the web, this part of the web, so these parts of the web subjected to buckling if the dimension exceeds some limits. This part of the flange in green are parts of the flange subjected to buckling if it is exceeding a certain limits. And due to that, if buckling happen, so this section will not be the location that has buckling will not reach yielding. Okay, so if the buckling occurs, let's make it occurs instead of happens. Some location of the members will not reach yielding. This means that we cannot consider in this formula, what is the formula? In this formula, we cannot consider all the cross-section area is under yielding because of buckling. So if the buckling happen, for example, here, let's make an example. So if the buckling happen in this part, so this will not reach yielding. So we cannot say that all the cross-section area will be will reach yielding in this case. To account for that, we need to find something called area effective. Area effective is based on or calculated using B effective. So we have effective width of the member. Effective width of the member give us effective area of the cross-section member or the cross-section of the member. So that's why the standard reflect on that using the factor Kf, and this Kf equal to, as you can see, the effective area over the gross area. If the effective area over the gross area is 1, so this means the whole section will reach yielding, and this means that no local buckling will happen in this section. But if, for example, like what happened here, if this area doesn't reach yielding, so this means that this is just an example, that AE over AG less than 1, so this means that the local buckling will happen or will occur in some points. Okay, so this is just a quick explanation of what is the meaning of the effective area and the effective width and the form factor Kf. So now how we can find the effective area AE? To find the effective area AE, we need to find the effective areas of the individual members whose effective widths are specified in clause 6.2.4. So to find AE, we need to find BE, or the effective width for the member. So how to find the effective width? BE using the formula for flat plate element with clear width B and effective outside. We don't care about the circular hollow section now. So for the member with flat plate like I-beam or channel and so on. So all this element, you can use this formula effective width. So the effective width BE of flat plate will be calculated using the formula, this formula here. So we have B effective equal to B, the width, multiplied by lambda E yield over lambda E. And as you know, B effective cannot exceed B. So the maximum is BE equal to B. This is the maximum value. So B effective, what we are looking for, equal to B, the original width, multiplied by this ratio. This ratio is the slenderness ratio. So to find the effective width, you need firstly to find the slenderness ratio. And to find the slenderness ratio, we need to know what is the lambda E and what is lambda EY. So the next part, as you can see, is the blade stiffness, blade element slenderness. So the blade element slenderness, lambda E equal to B over T. What is B? Width of the member. What is T? Thickness. As we discussed earlier here, the length of the member or the thickness of or the width of the member and thickness controlling the buckling or the local buckling. So this is reflected here in the formula. So lambda E equal to B divided by T multiplied by F yield divided by 250. So this is our formula. If you know B and T and F yield of the steel, so you can find lambda E. So B, clear width of the element outstand from the the face of the supporting plate. And for example here, if you have this I-beam, do you know what is B for the flange? B for the flange is from this part here. So this is our flange B in this case, and this is T. For the web, so this part here will be our B for the web, and this is our T for the web. This is what is meant by this part here. T is the thickness of the plate. So if you know B and T, you can find the factor lambda E or lambda effective, the slenderness of the member. Now, how we can find lambda EY? Lambda EY is,
Hey, sir. Sorry.
hello?
Yes. Can we go back to the previous slide, please?
Where is Ahmed? This one?
Yes. So I'm a bit confused why that shared point between the flange and the web is not considered in buckling, is it?
Yeah, because they are buckling means the free part of the member that can deform. But this part, you mean this part, right?
Yes.
Yeah, this part cannot deform because it is connected together. So this part of the flange from here, the free part, right?
Yes.
So this part is a free part, so it can deform and can deflect and can buckle and so on. But for the yellow part here, it cannot move because it's like connected to each other.
Okay, thank you.
Okay. So if we go back to our slide here, so this table here will give us the values of lambda EY. Lambda EY is the yield slenderness limits. So the yield slenderness limits based on the plate element type. So we are focused on flat members and the longitudinal EG support. So longitudinal EG support means if it is supported from one side or both sides. For our course or our steel design, flanges are supported from one side and web are supported from both sides. So if you look again here, this flange, part of the flange here or here, is supported from one side. But for the web is supported from both sides. And the next part is the residual stresses. So the residual stress based on the residual stresses are based on the manufacturing process of steel. If you remember week one lecture, we have steel, hot rolled steel and cold formed steel. Hot rolled steel, we need to apply high temperature to make the steel melting and then form it. For cold formed steel, we like cold form it or form it on the ambient temperature or the room temperature. So the residual stresses are mainly depend on the manufacturing process. So for example here, if you have stress relieved SR, hot rolled or hot finished HR, CF, cold formed HW, you can go to the table to find the other parameter. HW, for example, means heavily welded. So based on the type of the member you are designing, you can find the limit. So for example, if we are doing a hot rolled section, the flange will be the yield limit of the flange, or we can call it sigma E yield for flange, will be 16. And for web, HR for web, it is 45. So for web or sigma lambda EY for web is 45. So these limits are important for us so that we can check if it is buckling or not, and also to find the effective width and effective area of the member. Any question about that? Or good? So this was the section capacity of the members, and now we need to find the member capacity for the compression member. The member capacity is according to clause 6.3.3 for members subjected to flexure buckling or global buckling. So as we discussed earlier, the member capacity are concerned about member or global buckling. The section capacity is concerned about the local buckling. So the nominal member capacity NC will be calculated using this formula, which is NC equal to phi C multiplied by NS, and should be less than or equal to NS. So actually, the member capacity is a percentage of the section capacity. So that it cannot exceed 1. So the maximum limit of NC is NS if there is no buckling happen. So we can write it as a note here. If no global buckling occurs, what do you think will happen? NC equal to NS. So now let's consider what we need to find. We already can find this from before. So our rule here now is to find alpha C. How can we find alpha C? NS, again, nominal section capacity, determined as before. Alpha C is member slenderness reduction factor. There is two methods to find in alpha C. The first method is to find it using this formula. So alpha C equal to zeta 1 and so on, where zeta equal to lambda over 90 square and so on, where lambda over zeta. So this one is too complicated method because that we need 1, 2, 3, 4, 5, 6 formulas to find the value of the factor lambda c or alpha c, sorry. So we can ignore this method, or we can don't focus on it, and we have another method to find it. So we can find alpha c using tables. So alpha C using tables, you can see here. Here is the value of alpha C. So alpha C can be found using table 6.3.3 C. But we need some parameter to find it. So the parameters are lambda n and alpha b. So we can find lambda C, alpha C using table 6.3.3 C using two values, lambda n and alpha b. So let's know how to find alpha b and lambda n. Alpha b is the appropriate member section constant given in table 6.3a and b. So this is the first one for values of members, alpha b for members with kf equal to 1. What is kf? Kf is the form factor which equal to AE divided by AG. We know before how to find KF. If KF 1, so this means that no local buckling will happen, will occur. So depend on the type of member and KF equal to 1, you can find alpha B from here. So for example, if you are using hot format RHS or CHS, -1. For cold format RHS and CHS, -0.5. For hot rolled UB and UC with flange thickness up to 40, so this means that T flange less than or equal to 40 millimeter. So alpha B equal to 0. But if the hot rolled UB and UC with flange thickness over 40 millimeter, so TF over 40 millimeter, so alpha B equal to 1. So we can easily find alpha B using table 6.3.3a and the type of section we are using. If we found that KF not 1, because in some cases AE and over AG less than 1 means local buckling will occur. So in this case, you are using this table 6.3.3b to find alpha b. So based again on the section type. So for example, hot rolled UB and UC section up to 40 millimeter. So T flange less than or equal to 40 millimeter, alpha b equal to 0. And if it is TF, for example, more than 40 millimeter, so you can take it as 1. So based on KF, the form factor, and the type of the member, you can find the value for alpha B from this table. Is that okay? Up to here? So now, if we know alpha B. Can we find alpha C? Not yet, because we need to find lambda N. How can we find lambda N? Here is lambda N. So lambda N, if we add it here, equal to L effective over R root KF root F yield divided by 250. So this is the factor or the value of lambda N. So we know Kf equal to AE over AG. We know Kf. But we don't know, and also we know F yield. No problem with F yield. We don't know L effective and we don't know R. What is R? R is section probability or probability of section. We call it radius of gyration. The radius of gyration R equal to, do you know what is the radius of gyration is? Have you heard about it before? No? You should have learned about it before. Okay, so it is root inertia over area. So the radius of gyration R equal to I over A. If it is Ix, so this is Rx. If it is Ry, so Iy over A. So this is R, the radius of gyration of the section. And L effective is the effective length of the member equal to K effective times L. So for the radius of gyration R, no problem with R. If you know I and A, probabilities of member, you can find R. So R, no problem. KF, no problem. F field, no problem. So now we still need to find L effective or the effective length. The member length is already there, so we need to find the buckling coefficient for the member. So what is the only thing we need to find our target lambda n? So this is our formula, plus the formula to finalize the member capacity of the member. So the only thing we still struggle to find was LE. So LE is KE times L. So we need to find KE. So the effective length from the Stern standard AS 4100, we have two methods. One of them, before, yeah, just continue here. The formula first, again, L effective equal to K effective times L. So L effective equal to K effective times L. L, no problem. Co-effective is the buckling coefficient or buckling parameter. So how to find this buckling coefficient? Using two methods. The first method is like theoretical method, or member, we consider the member has idealized end restraint. The idealized restraints are the normal supports, pin supports, fixed support, pin supports, or free. or partially fixed or partially hinged. So if you have a column, for example, bin, I think you have seen before this. So this column, if it is under compression force, it will buckle idly like this. So this buckling length equal to KL, KEL. So K here is 1. So if you look to our table here, these values are given using the table here. So we have two cases, if the member in a braced frame or if the member in unbraced frame. So sway or unbraced frame. So if you are in a braced frame, we have two values, 0.7, 0.85 or 1. If the member is fixed at the top, fixed at the bottom, so 0.7, bin at the top, bin at the bottom, 1, and bin at one end, fixed at the other end, so it is 0.85. So these three cases are for what? For braced member. So you need to make sure when you start your calculation, if you are using this simple method, if the member is braced, so you need to take the value from these three cases. But if the member in a sway frame or unbraced frame, so we have three different value. So as you can see here, the three values of K are as follows: 1.2 or 2.2 or 2.2. So if the member fixed at the bottom and rotation fixed and translation free at the top, so it is to 1.2. So this support here, translation is allowed. So it can move horizontally. Because it is sway member, so sway member means the member can move horizontally. If it is fixed at the bottom, free at the top, so it is 2.2. If it is bin at the bottom and partially or translation allowed at the top again, so it is 2.2. So the yellow is for sway member, the brace is or the blue for the braced member. So based on the condition of the member, you can find what K effective. And if you know K effective, you can go back to here. So you can find what L effective, and you can find lambda n. If you know lambda n, so now if we know lambda n and we know alpha b, you can find what alpha c. So alpha c can be easily found using that procedure. And then we go finally back to here. If you know alpha c, you can find nc. So the calculation for the member capacity in compression is a little bit longer than tension because you need to find the parameter alpha c, which is a little bit complicated or lengthy in the, not complicated, but maybe lengthy in the calculation. So you need to go to this table if you are using the idealized end restraint condition. Another method, which is the accurate method for the K value, KE value, which is using this clause here, 4.6.3.3. So to find this value, we need to use two charts. One chart A to the left is for braced frame, one chart to the right for sway frame. So to find KE, you see KE here is one of these values on this chart. So to use this chart, you need two values. stiffness at end 1, alpha 1, or sorry, gamma 1, stiffness at end 2, gamma 2. So to enter these two diagrams or two charts, you need gamma 1 and gamma 2. If you know gamma 1 and gamma 2, you can easily, for example, if we have one here and one here, so you can find K effective is something between 0.8 and 0.75. So you can take it as, for example, 0.775. So this is just an example. So what is the problem, or what is the first step before going to the chart? We need to find gamma 1 and gamma 2. How can we find gamma 1 and gamma 2? The standard give us the formula for it. So gamma equal to summation I over L for the column over summation beta effective I over L for the beam. So C for column, B for beam. So what does this mean? Or how can we use this part, this formula? So if you are calculating the end condition for this column, for example, so we need to find gamma 1 and gamma 2. So gamma 1, we have two members connected, beam and column. This beam, you know its inertia and its length. This column, you know its inertia and its length. So the standard give us the factor gamma 1 equal to sigma I L I over L for the beams. If you have more than one beams, sorry, for the column, if you have more than one column over sigma beta E I L for the beams. Because the problem is, in some cases, for example, here, you can have beam 1 or beam 2 on the left, column 1 on top, column 2 on left. So this connection here can have more than one column and one beam. But for example, here in this case, we have only one beam and one column. So if you know I and L for column, so this can easily be calculated I over L. If you know I, L and I beam for the beam, so easily you can find I and L, IC, LC, IB, LB. So the only parameter we still need to know, beta E. What is beta E? Beta E is a modification factor. So beta E here is a modification factor that we can find from table 4.6.3.4. So if we know beta E, we can find gamma. So what is beta E? Beta E, again, we have two cases. One case for what? For braced member. Another case for what? For sway. So if you are solving braced frame, so you need to take the values here. If you are solving a sway member, so you need to take the values from here. Okay, so what is the values? And this will be last part. So fixity condition at far end of the beam. So it is a modification for the beam. So if you look to this beam here, so if you are solving or finding this column, the probability of this column. So the far end of this beam will be this end. So this is the far end of the beam. So the far end of the beam, if it is bent, so you take it 1.5. If it is rigidly connected to a column, so it is 1. If it is fixed, so it is 2. So in this case, this far end is rigidly connected to a column. So this means that beta E in this case equal to 1. So if you know IC, LC, IB, LB, and beta E equal to 1, you can find gamma 1. Okay, if you find gamma 1 and gamma 2, you can go to the table, the chart here to find the value of K effective. Okay, so this method is more accurate, and it is a requirement of the standard for frames. Okay, do you have any question, guys, for this part? All good? Okay, thank you for attending today, and I will see you in the class soon. Thank you, everyone.